Hi everyone, my name is Daniel, and today I'm going to talk about my recent work, which is titled Recoverable, Abortable, and Adaptive Mutual Exclusion with Sublogarithmic RMR Complexity. This is a joint work together with Adam Morrison. Let's start by talking about the model and preliminaries needed in order to better understand our problem. First, let's present the mutual exclusion problem. This is a very well-known problem which has been studied extensively for a few decades. In the mutual exclusion problem, we are interested in protecting access to shared resources by multiple concurrent processes. In the model of mutual exclusion, processes run in an infinite loop between four sections: the non-critical section, the try section, the critical section, and the exit section. A solution to the mutual exclusion problem, which is also called the lock, is providing the code for both the try and the exit sections. Recoverable mutual exclusion, which is also known as RME, is an extension of the mutual exclusion problem, which was first presented a few years ago by Gulab and Ramaraju. This problem was largely inspired by recent advances in NVRAM, which is non-volatile memory. In the normal mutual exclusion problem, most research has assumed processes are reliable and do not crash during execution, while in reality, this is not necessarily the case. In the RME problem, we remove that assumption. Instead, we assume processes might crash at any moment during the execution, and a process that crashed will eventually resume execution and will try to access the lock again. We also assume that such a crashing process, local cache memory, and program counter are initialized into their initial value, but anything stored in the main memory on NVRAM stays intact. Upon recovery, the process may execute a recovery section in order to properly recover from the cache and possibly use the information stored in the NVRAM in order to resume normal execution. A solution to the RME problem is providing the code for these three sections: the try section, the exit section, and the recover section. Another extension for the mutual exclusion problem is the abortable mutual exclusion. When a process is waiting in its try section in order to acquire the lock, it might wait an arbitrary amount of time until the process currently holding the lock releases it. In some scenarios, it might be beneficial to that process to be able to abort its wait and return to its non-critical section. A solution to the abortable RME problem is to provide code for the try, exit, and recover sections in a way that will allow a process in its try section to abort its wait and return to the non-critical section. A standard way to analyze the performance of locks is by using the RMR complexity, which stands for Remote Memory References. Each access by a process to a non-local memory word is counted as one RMR. We distinguish between two types of memory models: a CC, which is a cache-coherent machine, where every write access and every read access to a non-cached memory word is counted as an RMR, and the DSM machine, distributed shared memory, where every access to a non-local memory word is counted as an RMR. We also define adaptiveness. We say a lock is adaptive with respect to the point contention if its RMR complexity depends on k instead of n, where k is the number of concurrent processes accessing the lock as opposed to n, which is the number of processes the lock is designed for. When analyzing the RMR complexity, it is usually done based on a single passage of the process through the lock, meaning a run of the try section followed by a run of the exit section. In the RME problem, this is slightly more complex, since, for example, a process might crash in its try section and recover multiple times before successfully acquiring the lock. Therefore, when talking about RME locks, RMR complexities, it is usually divided into a passage complexity and a superpassage complexity. The difference between a passage and a superpassage can be seen in this illustration. A superpassage may contain multiple passages and starts when a process first tries to acquire the lock and only ends when the process successfully releases that lock. A passage on the other end might finish earlier, when a process crashes during the execution. Let's look at the following example. A process starts in its non-critical section. At some point, this process wishes to require the lock and executes its try section. At this point, this process starts both a passage and a super passage. At some point in the try section, this process crashes, ending its current passage but not its current super passage. Later on, this process recovers and executes its recover section. This time, the process doesn't crashes and is able to successfully run its try section, its critical section, and eventually releasing the lock. At this point, this process finishes both its current passage and its current super passage. We also define F to be the number of crashes a process experiences during a single super passage. Let's look at some recent work done on the RME problem. A couple of logarithmic locks were presented, which one of them is also abortable. This is the only other known abortable RME lock. A lock with sublogarithmic bound was also presented. This lock, super passage, had a multiplicative RMR complexity factor in F, which we will soon show how to improve to an additive factor. And lately, an algorithm with an adaptive bound was presented. But this adaptiveness was with respect to the number of total crashes in the system, which we denote as F star, which is not the standard adaptiveness definition that is with respect to contention on the lock. Our work has similar sublogarithmic bound to previous sublogarithmic locks presented, but has a better superpassage complexity and is both abortable and adaptive to contention on the lock. Some work with constant RMR complexities were also presented, but they either assumed a non-realistic strong primitive fetch and swap, a slightly weaker crash model called system-wide failures, or only an amortized complexity with an unbounded RMR complexity in the worst case. Our main contribution is the following theorem. There exists an abortable RME with RMR passage complexity of O of mean between k and log n in the base of W, where k is the number of processes accessing the lock concurrently, n is the number of processes in the system, and W is the size in bits of a memory word in the system, and has a superpassage RMR complexity of the same term with an additive factor in F, where F is the number of crashes a process experiences during a superpassage. The space complexity of the lock is O of n times W times log n in the base of W. Usually, there's a standard assumption that W is theta of log n, and in that case, O of log n in the base of W translates to be O of log n over log n. To give some context to our work, we look at the three based locks, which are a common design for both the mutual exclusion and the RME problem. In such a design, we first design a lock for a smaller number of processes, and then combine such locks in a static tree structure, where each node in the tree is an instance of such a smaller lock. Each process is statically assigned to a leaf in the tree. In order to acquire the lock, the process must acquire all the locks along the path from its designated leaf in the tree up to the root. In order to release the lock, it must release all the locks on the path from the root back to its designated leaf. In this work, we show how to use such a structure with an improved base lock in order to improve on several properties in comparison to previous work. So, to get an idea of how previous such trees were designed, let's talk about why is achieving recoverability hard, and specifically, why is it hard to achieve it in a constant RMR complexity. A standard solution with constant RMR complexity to the mutual exclusion problem is usually based on a linked list structure, where each process owns a node, and the node with the head of the list represents the current lock owner. In order to acquire the lock, a process must link its node to the tail using a fetch and swap operation. All processes in the list busy wait for their node to become the head of the list. Let's consider such a linked list-based mutex, with 3 processes already waiting for the lock. A new process now arrives and wishes to acquire the lock. The process executes a fast fetch and swap operation on the tail of the list, making the tail point to its node. The return value of the fetch and swap operation was node 3. This information now resides in the process cache, and it must write that into the main memory in order to complete its linking to the list. Assume this process now crashes. At some point, this process recovers and continues execution. At this point, the process has no way of knowing it has already executed the fetch and swap on the tail of the list, or that node 3 is its predecessor. Previous tree-based RME locks used linked list structures as their base locks, and they solved this problem by allowing a recovery process to fix the linked list state. The recovery was done by one process under an auxiliary lock. The RMR complexity of such a recovery is linear in the number of processes the lock is designed for, since it requires scanning all the possible nodes. Our work has 3 main contributions that, when combined together, prove our main theorem presented earlier. The first contribution is a deep process Abortable RME, which is an abortable and recoverable lock that has a constant RMR passage complexity and the super passage complexity of O of F for any D which is smaller than W, where W is the size in bits of a memory word in the system. Our main ideas in this lock are that we use the fetch and add primitive instead of fetch and swap, and that we design our algorithm in an idempotent way by 1. Never relying on the fetch and add return value, and 2. Allowing a recovering process to easily check if it already executed its fetch and add before executing it again. We then leverage this idempotency to design a simple recovery where a process can simply re-execute the section it previously crashed in. In our algorithm, we use a W bits word which we name active. This word represents W different processes by associating each bit in the board with a different process. A 0 bit indicates that the process is not currently accessing the lock, and 1 indicates it is. When a process wishes to acquire the lock, it sets its corresponding bit in its try section using a fetch and add operation on the word active. Note that the return value is not saved while doing so, and that we do not rely on it later on. Also note that each process can only set its associated bit by fetching and adding 2 to the power of k. And lastly, note the process only executes the fetch and add after first examining the active word and making sure its bit is not already set. A similar code to unset the bit back to 0 happens in the process exit section. In addition to the active word, we also keep the lock status word, which encapsulates the current state of the lock. Its first bit indicates whether or not the lock is currently being held, and if so, which process currently holds it, and what is its spin variable, which is a simple Boolean variable used by the process to busy wait in its try section. We also use a promote helper function, which is carefully designed to be idempotent and has 2 purposes. 1. Make some waiting process the lock owner, and 2. Signal to that process that it is the current lock owner by setting its spin variable to true. We call promote both in the try and exit sections. The way for picking the next process to be the lock owner is by examining the active word in a round-robin way in order to avoid some process starving. In addition to that, each process also maintains a status word in the environment. This word initial value is try, and it is updated by the process during execution when moving between its different sections. The process runs in an infinite loop of its 4 sections: the non-critical, the try, the critical, and the exit sections. Between moving from the try section to the critical section, the process sets a status value to critical section. And between moving from the critical section to the exit section, the process sets a status value to exit. When finishing the exit section, the process sets the status value back to try in order to prepare for its next superpassage. A recover function is a simple switch case function that relies on the process status word in order to make it return back to the section it crashed at and execute it again. In order to also make our RME lock abortable, a process is allowed to abort only while busy waiting in its try section. In order to do so, the process sets its status to abort and executes the exit code. In that case, executing promote in the exit code helps us prevent the situation where the process is made the lock owner while aborting its attempt to acquire the lock. Let's put it all together now. This is what the try section will look like. First, the process will check to see if its pin variable is already initialized or not, and will initialize it if needed. Then, the process will set its associated bit in the active word in case not already set. And then, will continue to execute the promote helper function, where it will try to make some waiting process, possibly itself, the lock owner. The process will finally arrive at its busy wait to wait for its turn to own the lock, where it can also decide to abort. If the process was made a lock owner and finish its busy wait, then it will set its status word to critical section and will move on to its critical section. If the process decided to abort before that, then it will set its status to abort and will go on executing its exit code. The exit code flow is as follows. First, if the process current status is critical section, then the process sets it to exit. Note that this means that if the process is executing the exit code due to an abort, it will not change its status. Then, similarly to the usage of the word active in the try section, the process checks to see if its associated bit is still set, and if so, will unset it. The process then executes the promote helper function and will then try to unset the first bit from the lock status to indicate that the lock is not currently being held. This is done using a compare and swap in order to ensure a process can only unset this bit if it is indeed the lock owner, which might not be the case if this process is aborting. Eventually, the process executes the promote helper function again in order to try and make some waiting process the lock owner. The reason for calling promote twice is done in order to properly handle the case of aborts, and the full details for this can be found in the paper. The process can then finish its exit code by deallocating its pin variable and set its status back to try. Our second contribution is our tournament tree, which has two main improvements over the previous RME trees. The first one is that we achieve superpassage complexity with an additive factor of f instead of multiplicity. And secondly, we define and satisfy a new property which we call superpassage wait-free exit. We achieve these two improvements by allowing a process accessing the lock to record in the main memory its current level in the tree during execution, and use that information upon recovery in order to allow the process to resume execution from that same level. Let's take a look at the flow of acquiring the lock. Assume some process tries to acquire the lock. In previous RME trees and in our tree, the process starts acquiring each lock node in the tree, starting from level 0, continuing to level 1, level 2, and so on. Assume this process crashes while trying to acquire the lock at level 2. In previous RME trees, upon recovery, the process first needs to reacquire every node along its path again, before recovering the lock at level 2. Also note that this recovery process does not have a constant RMR complexity, but it is in fact similar to the number of nodes in the process path. Only then can the process resume acquiring the rest of the locks along its path. In contrast, in our work, when the process can simply recover the node at level 2 and continues its execution from there. Combining the fact that in our node locks the recovery time is constant, and by allowing the recovering process to continue execution from the node it crashed on, we were able to reduce our superpassage complexity from a multiplicative factor in F into an additive factor in F. The flow of releasing the lock is quite similar. Let's look at a process that successfully acquired a lock, meaning it acquired all the node locks along its path, then executed its critical section, and can now start releasing all of its node locks starting from the root back down to its leaf. Assume this process is currently releasing its node lock at level 0 and crashes while doing so. In previous RME trees, upon recovery, the process must reacquire all of the node locks again before being able to release the lock. Note that this part is not necessarily weight-free, since it might be the case that some other processes have already acquired these node locks. This violates our new property we defined, which we called superpassage weight-free exit. In contrast, in our tree design, the process can simply continue execution at the level it crashed at, simply recovering it and releasing the node lock at level 0 to successfully release the lock. Our third contribution is a generic transformation to turn any abortable RME lock to an adaptive abortable RME lock by taking such a lock with passage complexity O of B and turn it into a lock with passage complexity of O of mean between K and B. The idea is to use a fast pass and a slow pass technique, where we use our D port lock with D equals W as the fast pass and any lock that we want to transform as the slow pass. When a process wishes to acquire the lock, it first tries to acquire a port number between 1 and W, using a loop of at most W comparison swaps. The attempt to acquire such a port number can only fail if K is greater than W, and in that case, the process falls back to use the slow pass lock. Eventually, we use a D port lock with D equals 2 in order to ensure mutual exclusion between processes that acquire the fast pass and processes that acquire the slow pass. This is a diagram of that flow. A process wishing to acquire the lock first tries to acquire a port number, which takes at most O of W RMRs, and in case it succeeded, it continues to acquire the fast pass lock, which will cause an additional constant RMRs. In case it failed, it will fall back to acquiring the slow pass lock, which will cause O of B RMRs. Either way, it will eventually try to acquire the 2 RME lock, which will cause an additional constant RMRs, and only then will proceed to its critical section. To conclude, we present our main theorem again, which we can now easily prove. We simply use our generic transformation on our tree-based lock, where each node in the tree is our D port lock with D equals W. Many questions still remain unanswered in the RME problem, and we are far from understanding how the recoverable model for mutual exclusion problem affects other properties of the lock. For example, worst-case algorithms have a sublogarithmic bound unless they assume an unrealistic primitive or a weaker crash model. Can this bound be improved without those assumptions? And if not, can a lower bound for this problem be proved? The best-known worst-case abortable mutual exclusion algorithm have a similar sublogarithmic RMR complexity. Can a formal connection between these two be made? These questions and similar ones leave room for future work on this problem.